Vectors in Rn. This chapter we're concerned about vectors, vector analysis, which is here an introduction. We want to connect the underlying, the undergirded mathematics behind most of all of the mathematics that we've considered even since kindergarten. And that is, what is the science behind the math of numbers? Numbers are said to form sets, and sets are said to form spaces and subspaces. And from those spaces, we have even what's called fields and groups, and these have particular definitions. All of this comes in the order of vectors, here vector analysis. The goal would be to, for this chapter and for this course, is to consider the idea of a vector space. From the vector space, we have a subcomponent that's called a subspace of a vector space. In that subspace, we're concerned with the idea of, are those sets or those vectors in the subspace, are they linearly independent? Do they span the subspace? If they do, then those vectors can form a basis. And we'll talk about what does that mean. And from all of that, we're then able to talk about how can certain vectors do things for us in the physical world, in terms of building, of constructing buildings or airplanes, cars, or whatever it may be. They are all said to be formed by vectors. We use computer technology to be able to graph and to pinpoint dimensions, which is nothing more than vectors. So in military strategy, we talk about missiles in projectile motion. We're still talking about vectors. When we consider functions are said to be subcomponents of vector functions. These are vectors that have function components in them. And so we can scoop and scale all of algebra, arithmetic, trigonometry, and calculus within one span of linear algebra. Also, differential equations is a subcomponent of linear algebra. Well, let's look today. Vectors in Rn. Rn is said to be the big space, the superspace here of, we call that nth dimension. We start with the first dimension, and that is R1. That is the space of all real numbers. In set theory, we call it Elif 1 or Elif null, that is. And the second space, well, the first space is just the space that just consists of one tuple, vectors, just one point. The two space, R2, two dimension, where we get length and width. And then R3, the third order tuples, the three tuple space, we get volume. So R2 we get area, R3 we get volume, and then everything above that is just make believe. No, each dimension can carry certain facets in terms of what the researcher is investigating. We can talk about the various facets of heat flow, and we can look at the pressure from heat, and all of these can carry certain dimensions as well. So, two of the strongest aspects of the idea of vectors would be one, how do vectors relate to each other? Can we add them? Well, we want to make sure we have it well defined in terms of the vectors in the space. Is the vector space, is it really a vector space? Because the vector space is defined on operations of vector addition and scalar multiplication. So can we add vectors? How do we add them? Is there a zero? Because if I add, if there's a zero, then I can get back to how I started. That is, if there's a zero, then there should exist negatives. If there's no zero, then how can you get a negative? If there's a 5 and if there's a 0, then it's possible that we can go from -5 to +5 and all in between. But if there's no 0, then how can I get the opposite of 5? It does not exist if there's not a 0, because the opposite of 5 is said to be split by 0. So let us look further. So the two essential components of vectors is one, how do we add them? And then secondly, how do we multiply a scalar to a vector? Well, you see the definitions there. The properties of vector addition and scalar multiplication in Rn. Let U, V, and W be vectors in Rn, and let C and D be scalars. So we have these 10 properties from algebra, or really from arithmetic. But no, they came from linear algebra. Arithmetic and algebra got them from linear algebra. See, you didn't know that you were considering linear algebra even back in first grade. So we have all of these properties that we will deal with very closely in the next section, because there, in order to prove that a set is a vector space, we must show all of these 10 axioms, or these 10 properties. And so the first 5 deal with addition, vector addition, and then 6 through 10 deals with scalar multiplication. Well, let's look further. Actually, in this section, there's only really one thing that I will consider. All the other aspects of this section is very elementary, and so I spared you with the homework with really only 2 problems. I could have given 10 problems of very simple things in terms of find the vector on the XY plane, or find the vector in R3, add the vectors, subtract the vectors, multiply the scalar times a vector. I think by now, I think we get all of that, and so I do not want to spend time with preliminaries as such. Here there are 2 very important properties: the additive identity and the additive inverse. The additive identity is said to be 0, and the additive inverse is said to be the negative of a quantity, the negative of a number. So if there is a V, then let there be negative V, right? And so if there is V, then does there exist? It's negative. The negative is called the additive inverse. Why is it additive? Because if I add the original vector to itself, then we get the additive identity 0. And if you notice, that's what's happening here with the additive identity of 0, and then the additive inverse property. So we have the idea of the additive identity, which is 0, and then we have the additive inverse, which is if there exists U, for all U in here, this big space Rn, there exists, it's negative. So there, the additive identity, which is the 0, and then the negative, or that is the additive inverse. Well, the only thing that I want to focus on is linear combination for this section, and then I'm through. Here, the linear combination is nothing more than if there's a vector, and here the vector is said to be x, can x be written as a linear combination of given vectors? Here the given vectors would be v1 to v sub n. So we say that a vector x is a linear combination of the given vectors if there exists scalars c sub 1 to c sub n such that x can be written. We just say that it's just x is written as a linear combination of the vectors. That is, that x can be written as c sub 1 times v sub 1 plus and so on, plus c sub n times v sub n. If this is the case, we say that x is called the linear combination of the vectors v1 to vn. Here's a problem. We want to write v as a linear combination of u1, u2, and u3 if possible. Enter your answer in terms of u1, u2, and u3. If not possible, then enter impossible, and that's over in Web Science. So if here v is a linear combination of u1, u2, and u3, that means that there exist scalars c1, c2, and c3 such that the linear combination of these vectors and scalars, that is c1 times as u sub 1 plus c2 times u sub 2 plus c3 times u sub 3 is equal to v. That's the question. All right, is that the case? Now, that looks like here that this c1 is times the vector u sub 1, and that's 2, 1, 5, plus c sub 2 times u sub 2. Now the vectors naturally want to stand up, because any person ought to want to stand up. times u sub 3, negative 3, 2, negative 4. Is that equal to v? And v is negative 1, 7, and 2. Now watch this. Now when you work this out, we have a matrix. I hate that cursor, but I'm not going to spend time trying to get rid of it. I'll probably lose the whole thing. So I have this system. So you're going to use your graphing calculator and just solve it. See if I can pull mine up. So I'm working with this is the TI 89. So what I've done was to put this in my graphing calculator. For the TI 89, here I went to second and then math. That's the digit 5. Above that is math. Okay, seems like that guy doesn't want to open up for me. Well, that's working. Oh, the cursor needs to be there. So maybe home. Okay, well, anyway, I get back to that. I went to second and then math. How come that doesn't open? That's beyond me. And it gives me these list of options. I want to choose matrix, and then from the matrix, I choose RREF. That's row reduced echelon form. And I think if I click on that, it should show you how I entered those in. Let's see. Yeah, there they go. So the graphing calculator is going to give you in the default the opening parentheses, and you have to supply the open bracket. Now when you put the numbers in there, you have to put them in with respect to the row. So I had to put in the 2, 3, negative 3, and 1, each one separated by a comma. Now here they close up with brackets, but I didn't do that. I just used semicolon to close that up. And then I start the next row, 1, comma, negative 2, comma, 2, comma, 7, and then semicolon, and then the next row, 5, 4, negative 4, and 2. And then after I did that, just hit enter. And when you hit enter, it solves it for you. See if I can pull this down. So notice that that solution there of that that matrix reduction. Oh, let me pull it back up. So it's 1 0 0 0. And then it's, I think that was 0 1 negative 1 0 0 0 0 and then 1. Yeah, I think that's right. Let's make sure. Yep. Now what does that mean? That means this, that C sub 1, because that's what you're solving for. C sub 1 is equal to 0, which is okay. We have sticky issues here because that second equation row says that C2 minus C3 is equal to 0. Can't do too much with that. We get basically C2 is equal to C3. So you get an infinite solution there. But the trouble is I get 0 equal to 1. Now that's impossible. So there exists. So here the question is, does there exist C1, C2, C3? No. There does not exist C1, C2, C3 such that these three vectors form a linear combination of the given vector. So there you want to make sure that you say that was impossible. And I think the one in the homework, unfortunately, I think it's impossible. You would think that they would kind of change that up so you get maybe different answers. So, but anyway, I can show you another problem where we actually get something. Okay. So for this particular problem, we must find scalars. We got three vectors, u1, u2, u3. So we must find scalars c1, c2, and c3 such that, is it true that c1 times u sub 1 plus c sub 2 times u sub 2 plus c sub 3 times u sub 3 is equal to v? Well, it's still the same setup. We have u sub 1 times that first vector of u sub 1, so that's 2, 3, 5, plus c sub 2 times the second vector, 1, 2, and 4, plus c sub 3 times that third vector, negative 2, 2, and 3, equal to v, which is 10, 1, and 4. Now, that's the matrix is just 2, 3, 5. You can kind of see how that goes, that each vector is a column for your matrix. Now, in your graphing calculator, you just do the RREF, and for that one, when you do that, let's see, what did we get? That's that guy right there. Let me pull it down so you can see it. I have the big view for the calculator because typically it's very small and I couldn't hardly see it. So that is, you get the 1, 2, and the -3 on the far here on the far right. 1, 2, and -3. So that simply means that C sub 1 is 1, C sub 2 is 2, and C sub 3 is -3. That means that the vector V is written as 1 times that U sub 1, which is 2, 3, 5, then plus 2 times U sub 2, 1, 2, and 4, plus the -3 times U sub 3, which is -2, 2, and 3. Let me just check that. So we just go across. That's 2 plus 2 is 4. And then that's 4 plus 6 is 10. Then this is 3 plus 2. Well, it's 2 times 2 is 4. That's 7. And then that's 7 minus 6. We get 1. And then this is 5 plus 8. We get 13. And then 13 minus 9 is 4. And so that gives us the vector V. So you can see the scalars here, 1, -2, and -3. Which came right from the solution of the matrix. So that was the whole idea for chapter 1, and being able to solve a system so that we can now connect that to the to vector analysis. Okay. Well, I'm going to let that do it, and you all take care.